Uh, yeah, I hope I'm audible. Can one of you please confirm? I am audible, right? Yeah. Okay. Thank you. So the topic for this week was SVMs, and so SVMs are like before the neural networks and everything. SVMs were the one. SVM was the architecture which was, or rather, the algorithm that would be used for most machine learning most machine learning tasks. So in that sense, this is a very important and very elegant algorithm also. So this week was all about that. So as I've done in the previous weeks, and as has been told to us by NPTEL people, like we'll go through the questions which were given in the last year's assignment, and so there are some coding questions here as well. So I'll go through there are 7 questions in all, four of which are I'll work out, and the last three will be coding. So they will be simple coding questions. So just I guess you will get a feel of how to code these in Python. Okay, so and if you have any doubts in between, you can stop me. And towards the end, after I finish the questions, if you have any doubts in general about SVM, what was taught in this week, you can ask me after the questions are over. So, okay, so let's get started. So my screen, yeah, it's visible. Okay, so the first question that is, it says that consider a one-dimensional data set. So it has, these are the features, and y is the output, and the data set becomes, a statement has been made that the data set becomes linearly separable after using basis expansion with the following basis function. So that means that you give some x, I mean these three x's you give to this phi x function, and then you try to see whether it becomes linearly separable or not, because linear separation is something that you want. So let's see what happens if I pass phi minus 1 to it. So phi minus 1 would become 1 and minus 1, right? So because any x after being passed to phi x becomes 1 and x cube. So 1 remains 1 and x cube becomes minus 1. Similarly, phi of 0 becomes 1, 0, and phi of 2 becomes 1 and 8. So these are the 3 points in the new basis that you have that has been given to you. And in order to find out, okay, can somebody just looking at these 3 points, can you tell whether they're linearly separable or not? These are our two-dimensional points. So can just by looking at them, can you figure out whether it is separable or not? Okay, I don't see any. Okay, see, just by looking at this, you can understand that all of them are along the are all of them are parallel to the y-axis, right? Because all of them has the same x coordinate, so they can't be linearly separable. So if you want to see a visual reason, I mean, I can show you a visual thing for that. Let's see. So let's say this is x equal to 1. So the first point is minus 1. So the first point is somewhere here. Okay, the second point is this one, which has 0. So it has a y of minus 1. So the label of that is minus 1. I'm denoting that by cross. And the third one is again of the same class as the first point, and it is somewhere, suppose this is 8. So it is somewhere here. It is somewhere here. So these are the 3 points, and by no means you can draw a linear classifier which would put these two circles in one direction and in one side of the linear classifier of that line, and the cross on the other side of the line. and therefore there cannot be any linear. So these points are still not linearly separable after this particular basis expansion. So the answer for this would be false. Okay. So if you have any doubts, you can stop me. I'll just go ahead with the questions if you don't stop me. Okay. Okay. Then consider a linear SVM which is trained with n labeled points in R square without slack penalties and resulting in k equal to two support vectors where n is greater than 100. By removing one labeled training point and retraining the SVM classifier, what is the maximum possible number of support vectors in the resulting solution? So without any more information that has been given in this problem, I mean, one iteration of SVM has resulted in two support vectors. That doesn't mean that, after that you have changed the dataset also because you have removed one labeled training point. So you really don't have any reason to believe that it will be close to two, like it will be one or three. So the answer is, so if you have gone through the lecture, it has been mentioned in the lecture that potentially all of your points can be support vectors. All of your point can turn up to be the support vectors of your resulting SVM. And therefore the answer would be n minus 1 because you had n labeled examples and you have removed one. So you have n minus 1 points remaining and therefore n minus 1 would be the correct answer, right? Okay. So after that, which are the valid yeah, so the last one is like, okay. Yeah, so the last one is like, if you have n training examples, your support number of support vectors can at most be n. Okay, all of your points can be support vectors. Okay, so here it is the first part of the question is really not much informative because it is only, I think it is only given to maybe confuse you a bit in the sense that if you have n greater than 100 and you have two support vectors in one iteration of this, I mean after running SVM for once, then that is an information. But once you have removed one label training point and retrained the SVM classifier, you can potentially end up with all the other n minus 1 points being classified as support vectors. And therefore, the second once what is the maximum possible number of support vectors? It's still n minus 1. Okay, because number of training examples, all of them can turn out to be your support vectors. So since you are training with n minus 1 examples, you will have the maximum possible number of support vectors would be n minus 1. Okay, is it clear now? Hello. Okay. Okay, so the next question is just directly out of the lecture. Like these are the three kernels which were introduced in the lecture, and you would know that all of them are valid kernels. The first one is a polynomial kernel. The second one, I think, uh, is it's a 10H, but it's actually a sigmoidal kernel. It's called a sigmoidal kernel. And the third one is the RBF kernel. So the RBF kernel is the most widely used one. Yeah, polynomial ones are also used, but in general, you would most likely use RBF kernel if you are working with very complex data sets. Okay, so the last question, which is like theoretical, and we have to work it out in that sense is now consider an SVM with a second order consider the SVM with a second order polynomial kernel. Kernel 1 maps each input data point x to x and x square, right? And kernel 2 maps each input data point x to k2x, which is 3x and x2 square. So they are more or less the same, except that one is a scaled version of the other 3 times. So assume that the hyperparameters are fixed. All the other hyperparameters that you train your SVM with, they're kept constant. Which of the following options is true? The first one says the margin obtained using K2x will be larger than the margin obtained using K1x. The second one says the margin obtained using K2X will be smaller, and the last one says they will be same. What do you think? Which is the correct answer? Can one of you try? Okay, I'm not getting any response. Okay, how to say this? Okay, let's say. I mean, if you remember how margins are, so let's say you are doing a two-class classification, a very simple case. So let's say these are your classes. I mean, these are your training examples, let's say, and this is the decision boundary that you have learned, and this is the okay, let me put another point here, right? Yeah. So this is your margin. Okay. This, I mean, the from the decision boundary, the closest point for both the classes is your margin. So if you see here, everything is same except that one is three times the other. The second kernel is three times the first kernel, and therefore any distance which comes from the first kernel it will be multiplied by 3 in the second case, because kernel to any x and x square, if it is any point which is being mapped to x and x square by the first kernel, is equivalently mapped to 3 times that point in so if this is the point that was, suppose this is the point which was mapped to by k1 x, then the corresponding point which will be mapped by k2x will be 3 times. I mean, it will be much higher. Let's say it will be somewhere here. So this is the point that is mapped by k2x, and therefore the margin also will be equivalently much larger. It will be exactly be no, it might not be exactly 3 times because of certain other ways in which this margin is being calculated, but it will be larger than the margin obtained by k1x, right? So the first option would be the correct one. Okay. Yeah, so with that, we come to the end of the theoretical questions. Now, the rest, the three questions, they're all coding questions. For that, I will I will share another screen. So, I don't know how to show this. Okay, I'll just give you the questions maybe from here, but I can't dual share. Anyway, okay. Let's see. So the first question is, consider the following data set. So this question is actually wrong. This question, I mean, there is, I'll come to it. So, okay. So you have 10 points, no, you don't have 10 points. You have 8 points, 1, 2, 3, 4, and 7, 8, 9, 10. And you have the corresponding class labels. Which of this is not a support vector when using a support vector classifier with a polynomial kernel with degree 3, c equal to 1, and gamma of 0.1, right? And the question also mentions that we should use sklearn for this particular question. So actually this would be the not won't be there, because which of this is a support vector when using a support vector classifier should be the question. So so for this, let me switch over to my other screen where I'll show you how the code is being done. So I'll stop sharing from here and just give me a minute. Okay. Hope this works. Uh, yeah, can you guys see my code? I have opened Google Colab, so can you guys see that? Zoom in. Okay. Uh, is it fine now? Hope it's fine. Okay. Let me see. Okay. Yeah. I'll reconnect. So this is some of you might already know about this. This is something known as Google Colab. So you will just need a drive, and you can get GPU access here. But we don't need GPU for this. Okay, once it connects, I will be able to work on this. Maybe let's see how much time it takes to connect. It's taking a lot of time to connect also. It will come now. Okay, so the first step is not important. Very slow. Okay, so here I'll come to the packages. I mean, the first package is used for it is used for reading, doing a number of things. Here I will use it for reading CSV files for the next few questions, not for this particular question. And for okay, yeah. So for this particular question, we'll just need these two functions. Like we'll need the from sklearn.svm import svc, which is a support vector classifier, and we'll also require the Python computation, the matrix computation package that comes with Python, which is known as NumPy. So these two packages we'll need. And okay, so coming to this classifier.algo, let's first look at what sklearn tells about the classifier. Yeah, so this is the sklearn's documentation. Yeah, it has opened now. So let's say I have so it is a C support. So it's based on some other implementation, but these are basically the things that you need to find out. So C is the strength of regularization is inversely proportional to C. C must be positive. Then kernel, you have these linear polynomial RBF sigmoid. RBF and sigmoid. Degree is generally it will only be used when you have the polynomial kernel. Gamma is used for RBF kernels mainly, but polynomial and sigmoid kernels also use them. But it will they are not important for polynomial or sigmoidal kernels. Mostly they will be used for RBF kernels. Then coef 0 independent term, it is only significant. So that is the 1 plus x1, x2, or you can have 0 there. So it depends on that. Shrinking and all those things, generally people generally won't use all these things. But another thing is this decision function shape. So if you remember, if you have gone through the lecture, you would know that what SVM does is it tries to differentiate one function, one class from the other. Now you can have multiple classes. For example, you can have more than two classes. You can have three classes in your problem. In that case, what you generally do is you do one versus rest, which is OVR, which stands for OVR, one versus rest, and the other is original one versus one. So one versus one is like it will take NC2 sample NC2 ways in which you can select two classes from those n classes, let's say. So it will learn NC2 different classifiers, and for OVR it's much better because it will only learn n classifiers where only one class will be considered as positive, all the other classes will be considered as negative. And in that way SVM will try to find out, so n different models of SVM will be trained, And yeah, so that is about OVR, decision function shape. Okay, and the others are not necessary for now. So let's go back to the code. So as I showed that SVC is the support vector classifier, C equal to 1 is the constant. We have been told to use the polynomial kernel of degree 3 and gamma equal to zero point 0.1. X equal to NP array, that is your input training data. If you remember, this was the data that was given to you. This is just for because SVM expects it to be expects it in a particular format. That is why this none is given. Y equal to np dot array is the labels, and then what you do is you again go back to the SVC classifier, and you see here that how they have done is this pipeline and all these you don't consider now. So once you have designed the classifier, you just put clf.fit. So clf is your classifier which you have created, and once you have done that, you just fit the x and y. So x is your input, y is your output. So you can do that directly. Classifier algorithm dot fit x comma y. You have got the x, you have got the y, and after that, what? And here the question was which one can be a support vector, right? So if you see here in the attributes, there is something known as support vectors. This will return the support vectors that is actually present, that has been computed by SVM for your particular data set. So the support vectors which are used will be returned by this particular attribute. So that is what you will be doing here. So let's run this and see what happens. See, you have four support vectors. So for your four support vectors, you have 4, 7, 1, and 8. And now if I again share my original screen, yeah, 4, 7, 1, and 8. So the question, as I said, was slightly wrong. 1 is indeed a support vector. In fact, 3, 9, and 10 are not support vectors. So if this is the question, if this is the question, then the answer would be 3, 9, and 10. If which is not a support vector is a question, so which of this is a support vector is a question, then one would be the answer, as we just found out from sklearn. Okay. So yeah, finding the support vectors is something which you can't really do just by looking at the data set, because it will be very difficult, because these polynomial kernels and all those things are there. So it's best to just go to sklearn, do whatever the question has asked, and find out what the support vectors are. Okay. For the next two questions, they have asked us to download some dataset. So this dataset is iris dataset, and the dataset contains 150 points, and each input point has 4 features and belongs to one among 3 classes. So here there are 3 classes. The last one, there were only 2 classes, 0 and 1. But here there are 3 classes. Use the first 100 points as the training data and the remaining 50 as test data. In the following questions, to report accuracy, use the test dataset. You can round off the accuracy. Again, we have to use sklearn for this, because otherwise, of course, this is a coding question. So the first question is train a linear perceptron classifier on the modified iris dataset and report the best classification accuracy for L1 and elastic net penalty terms. So that is the first question. And the other is train an SVM classifier on the modified iris dataset. We encourage you to explore the impact of various hyperparameters. You probably won't see much change because this is a very simple dataset. But anyway, you can try and specifically try different kernels. As part of the assignment, train models with the following set of hyperparameters. So the hyperparameters is gamma is set to be 0.4. The kernel is poly 1 versus rest classifier. No feature normalization needs to be done, and try C equal to. So I'll stick with C equal to 10. For the above hyperparameters, report the best classification accuracy. So these are the two problems on the same dataset that has been asked. So now let me go back to the okay. I'll stop Sharing. Okay. Yeah. So what I've done is, if you go to that link which has been given, what you will find that irisx.csv and irisy.csv, and this is why I downloaded. I had okay, somebody is joining. Yeah, so I have downloaded those two CSV files into my drive, and I'm reading that. So what I'm doing is I'm reading the CSV files. There is no header in the CSV files. That is why that header is set to none. There is no header in the CSV files. That is why the header is set to none. And finally, I'm converting them to NumPy arrays, both X and Y. So let's just comment out this and see what happens. So X is of shape 150 cross 4 and Y is of shape 150 cross 1. And now the first question is perceptron with a penalty of L1, with L1 regularization. The first 100 points will be used to train the classifier, and the next last 50 points will be used to test the classifier. Okay. So if we do that, then if you see, if I run, yeah, you see there is something which is a warning is coming. It's not precisely an error. So what it is saying is a column vector y was passed when a 1D array was expected. Please change the shape of y to n samples, comma something. So this is a strange thing that sometimes happens in Python. It will not give you errors in this case, but is generally better whenever you see any sort of this error. You should always do something like this. The one line that I just commented out, you remember how y the shape of y 150 cross 1. Now after doing this, you will see what the shape of y is. It is 150 cross, comma. So exactly in the same way which sklearn has asked me to provide y. So after running this, you will see that there is no such error. So it is just a warning for this case. The answer is not changing, but it is always a sanity check to see if these warnings are arriving. You might land up into bigger problems. If your problem is complicated, this might lead to bigger problems. So that is the first question, like perceptron penalty of L1. The other penalty is elastic net, which is a combination of L1 and L2 regularization. So again, I'm doing the same thing. I'm training a classifier, perceptron classifier with elastic net regularization. And what I'm doing is I'm fitting the first 100 points for training, and taking the next 50 points for testing. And once I do that, it comes out to be 0.82. So elastic net, so regularization is probably not required in this case. That is why once I'm using the L2 regularization, the test score is dropping. The last question is, if I use a SVC classifier, and let's just stick with c equal to 10 for now. C equal to 10, kernel is the polynomial kernel, decision function shape is OVR, gamma equal to zero point 0.4, and I'm doing the same thing. I'm fitting x at the first 100 points for training, and the next 50 points for testing. So once we do that, we see that the answer is 0.96. And so these are the two answers. So these are just simple, very, very simple. I mean, it won't get simpler than this. So if I try changing the kernels, let's say I am going to c equal to 0.1. It is not changing. 0.01. Okay, let's just look at C. I hope it's the same C. Regularization parameter. The strength of regularization parameter is inversely proportional to C. So I'm increasing the regularization as I decrease C. So even then it is happening, it is coming out to be 0.96. Now if I decrease C further, see, at this particular point, we have seen an increase in the test score, which means that the generalization is getting better. So 0.001 is actually better. It's coming out to be 0.98, right? Let's see what happens with 0.001. That also is 0.98. Now all of a sudden you see it is coming out to be 0.88 because you have regularized your SVM classifier so much that it is not being able to train properly. I mean, it is not being able to learn the training data itself. You have over regularized, and after this, if you increase more, I guess it see it's coming out to be 0.64. So if I decrease it more, it's 0.32. Okay, I hope you get the idea. So, and let's just check with RBF kernel. It's still 0.32. It's not, it's still 0.32. Okay, it won't help. That means RBF kernel is not, it's a very powerful kernel, but in this case, it is not being able to do anything. RBF kernel is not working at all in this case. For c equal to 1, it is again 0.98. Okay, so C equal to 1, the polynomial kernel had given 0.96. The RBF kernel is slightly more complex than the, not slightly, it's much more complex than the polynomial kernel, and it's giving 0.98. Yeah, so this is how you can play with the different parameters. The best thing to do would be to go to sklearn.svm.sbc, look at the different things that you can do with all these, and you can play around. I mean, you can just go into sklearn and it will also give you some standard data sets, how to handle some standard data sets, and that is how you can work on all these. Okay, so yeah, so let me stop sharing this screen, and let me share the other screen. Yeah, so I think for the second question, the answer was 0.96, and for the first question, I've forgotten. It was 0.84 and 0.82, as we have seen in the. So this code and everything, I will give it to you in my. I will give that link to NPTEL people, so you will be able to access that. Yeah, so that is it about the questions. Now, if you have any more questions, you can go ahead and ask me. Okay, anybody has any questions? Okay, if you have no more questions, then I can close the call. I guess these all these things are easy for you all. Yeah, so it's fine. I mean, okay. So if there are no more questions, I'll close the call. Yeah, there is a lot. Suddenly, there was a lot of noise from some place. Somebody. Hello. Hello. Yeah. Yeah. No, it was not my session. It was somebody else's session, I think. From. Oh, I don't know. I don't. I don't know about that because that is somebody else's session. Yeah. My sessions are always at 7, yeah, 7 to 9. No, that is the best accuracy. I mean, the parameters which has been given with zero point 0.4, one versus rest classifier, and no feature normalization. With that, we got with all these points, the best accuracy that we got was 0.96, which is yeah, something point zero. I think it is 0.001 or something. Yeah. Yes. So yeah. So basically, what happens is. Um, So if you remember in SVM there is a formulation which is the also called the soft formulation. So like you can this is your normal SVM, right? If you have classes like this, if your data points are something like this, then the normal SVM would say that okay, all of my points. So okay, this has to pass through this point anyway, but your margin, this is your margin, and all of your points will be on the correct side. So this margin is sorry, this is not the margin. Sorry, very sorry. This is not the margin. Yeah, this is the margin, the half. So this is your decision boundary. Okay, this is the thing that you learn in SVM. So yeah, yeah. It has to be equidistant. It has to be equidistant from both. See, if see, so like, so you are saying something like this, right? So you are saying something like, uh, okay, how to draw this? Okay, you are saying something like, um, something like this, is it? So in the, yeah, yeah, hmm, hmm, yeah. They have to be equal. That is something that you need to remember. They will always be equal from both the classes. Okay. So that is why M can be that is the reason why you can define M from either of the two classes. It doesn't matter from which class from which class you compute the distance, because they would always be so the nearest. So if you are just looking at this and finding it difficult to understand which are the two nearest points, such that the margin would be in such a way that this line is equidistant from both the classes, you can always rotate the line. It need not always be straight. I mean, it will almost never be straight, right? It can rotate like this line is rotated in this sense. So in this way also you can get your margin. So here also it will be equidistant from the midpoint, from the middle line. Okay. Correct. Exactly. So yeah, last part I did not get. Hmm. Your voice is somehow getting disconnected in between. I just heard, sir, can you, and then then I couldn't hear you. Yeah, I can hear. Yeah, I can hear you now. Yeah. Yes, yes. Yeah. Correct. Correct. Huh. I'm not. Uh, I don't think I understood your question. So if you're asking like, so for example, if your class distribution is something like this, and there is another point here, and all the other points are here. Are you asking something like this? Like what will happen in this case? Hmm. Hmm. This point can move here, is it? Left. Okay. And this point. Okay. Yeah. Huh. Yes. It might change it. It depends on your hyperparameters also, right? Like for example, I mean, it is very difficult to say what will happen in this case. It might be like this. Okay. In which case, in which case this point might be the closest, or this point actually will be the closest, I guess. I am not sure. I mean, this is. I'm just so this point may be the closest, and this point may be the closest for that. Okay, so it all depends on how you on your different hyperparameters that are there in this particular that you are training your SVM with. Okay, so it's yeah. So your question was something different. Yeah, your question was something about C, the parameter C, right? Yeah. So if you remember, like this is the central line, this is the mid line, and so on both sides of it there will be the margin from where all the different questions came. Like the margin would be equal for both the classes. Okay. So there is a single, that is why there is a single margin definition in SVM. Otherwise, if margin were different for the two different classes, then there would be, depending on the class, you would have a different margin. So always there is a single definition for margin because margin is same for all the classes. Yeah, go ahead. Uh, Yes, yes, yes. D1 should always be equal. So you can either max. So basically, what you need to do is you need to find out the closest points from both the classes, and you need to maximize that distance. Okay. And so then you do, yeah. So this is the normal SVM formulation. In this case, you are saying that any point you cannot have any point which is either in the margin, right? Which is either in the margin, and I mean, either in the margin means there can be no point here, and also there can be no cross towards this side. This is not allowed. This thing is not allowed. Similarly, there can be no circles on the other side. This thing is also not allowed. Yes. Yeah, so what then happens is, but this is a very, what should I say, very strict way of treating any machine learning points, that you can't have any misclassification on your training data, right? And if you think that very deeply, in some sense, that is the precise definition of overfitting. So overfitting means you have completely memorized your training data. You have memorized your training data in such a way that you can't generalize to test data, right? So if that is the case, then okay, so that is the way normal SVM works, but then SVM again would be very prone to overfitting in that case. So then what happens is they introduce, if you remember, they introduce certain variables called slack variables, which is denoted by zeta, and the value of zeta will be positive. always greater than equal to 0. Now if zeta turns out to be if zeta turns out to be 0, that means that classifier, that particular this particular point is correctly classified. If zeta is greater than 1, that means the point is misclassified. And if zeta lies between 0 and 1, it is in the margin. But I mean, those details I don't think was covered in the lecture, so I won't go into those details. So this C, which is there in which is there in Escalon's SVM, this is directly proportional to this, and or not proportional to, this is directly linked with zeta. So what happens is this is your normal SVM objective function. You add with that C times I've forgotten, I think C times zeta, summation zeta or something, is it, or something else? I think it's C times summation zeta. Yeah, C times summation zeta I, where zeta I exists for all the points. Now, what you need to do is, if you see here, if you just you forget the other classify, you forget everything that is in the constraint. You just look at this and see that if C is, and you are trying to minimize this. Okay, this is a minimization problem. So suppose C goes to infinity, right? C is very large, so you can't obviously do infinity, but C is very large. In that case, if you put yourself in the place of optimization solver, so what it will do is, it will see that C is infinity, so I better put all the zeta is to 0. Am I correct? Suppose that is different. That comes later. I am saying that precisely from object from the point of view of an optimization solver, you are trying to minimize this particular thing. This circle, this square rectangular thing which I have shown here. You are trying to minimize this, and you have put C equal to infinity. So what do you think the optimization program will try to put the value of zeta to? Minimum, yeah, correct, right? It will be 0, right? Now, since it is 0, you already know that the way that you have defined zeta, whenever zeta turns out to be 0, that means you are back with the original formulation of SVM. And with the original formulation of SVM, you have no regularization. You have to do everything correctly on the training data, correct? Now, if you decrease C, then your, yes, yeah. Regularization is inversely proportional to C. That is why, if you remember, like when I am putting C down, which is like I am going it, I am making it 0.0001. That means it is regularizing slightly, and that is why it is being able to increase the test accuracy from 0.96 to 0.98, because I am introducing slight regularization. However, if I decrease it to this value, this particular value, you saw that then what happens is, then many zetas can be non-zero, because C is very low now. So many zetas can be non-zero. That means it is not even being able to learn the training data properly, and therefore the accuracy dropped to 0.32 or 0.64, whatever, I forgot, something of that sort. When C was very low, it came down to 0.32 or 0.64. Why did that happen? Because then C being very low, the SVM solver put many zeta is to non-zero values. As soon as it became non-zero values, that it couldn't learn the training data also. So as soon as it stops learning the training data, it obviously won't be able to do well on the testing data, right? Yeah. When C is uh, when C is very low, when C is this particular value, 0.001, then did my test accuracy increase or decrease? It got increased, right? From 9.6. Huh. So regularization, just by looking at the test accuracy, is very difficult to judge, because over regularization will also decrease your test accuracy. Okay. Yeah. I hope that was clear. Any more questions? Huh, huh. Uh, yeah, SVM is actually a difficult topic. SVM is not very easy to grasp. And but however, SVM, if you understand, it is a very elegant way of classifying. I mean, it's a very powerful way of classifying classification. So try to understand SVM. Yeah. Yeah, actually, for SVM, this particular how this problem is solved, that is not in a code. I mean, that is not within the scope of any machine learning course. That is a complete optimization problem. So you don't need to worry about how to solve this. You just need to get an idea about this particular value of C. Okay. Uh, this particular value of C, what it does, what its role is in SVM. Then all the zeta i's. Of course, if you understand C, you will have to understand zeta I. Yeah, and the different kernel functions and kernel trick. I mean, there is a separate lecture on kernel trick, I believe. So kernel trick, if you understand, then I think rest of SVM. I mean, all these are details which cannot be covered in a first course on machine learning. So these three, four things, if you keep in mind, then that is enough for SVM. Yeah, thank you. Any more questions from anybody? Okay, if there are no more questions, I'll close the call. Next week, I believe, is about neural networks. So we'll meet again next Saturday, the same time, 7 p.m. Thank you. Yeah. I am going week by week. So this is the fourth week that I am meeting with all of you. So that is why I'm looking at the week four lecture and trying to and telling that in the lecture. So yeah. Huh. Hmm. Oh, that might be a problem because I am already then 1 week behind. Uh, I don't know. Then let me check with the other TAs in this course, and next week I don't know, because I am following the same way the lecture is going on. So week from week one, week two, week three, and week four. So this is the fourth time that I'm meeting, and I'm covering the lecture and covering the material of week four. So I don't know why you have been asked to submit week five now, because maybe we are for the PMRF students, we are getting 1 week lagged behind, because we started also 1 week later. Maybe because of that this is happening. Hmm. Okay, I'll try to do that next week. But then that what happens is that last week, what will I do? Okay, let's see. Okay. Neural networks assignment submission is when? This coming Wednesday, is it? Okay, okay. Let me check with the other TAs also what they are doing, and I'll update accordingly from next class. Okay. Yeah.